Okay, so now we want to do a more quantitative question using Bernoulli's equation. In this case, water travels through a pipe at 8 meters per second. The pipe expands from a radius of 1 meter to a radius of 2 meters. So how does the pressure change from the 1 meter radius pipe to the 2 meter radius pipe in kilopascals? The density of water is 1,000 kilograms per cubic meter. So this question has a bunch of steps. Your version is scaffolded out more, but it's pretty much the same problem. We have a pipe that has water flowing through it, and the radius of the pipe doubles. First of all, watch out. We have increased the radius, so we haven't given you the area. The area of a circle is pi r squared, so that means that the area of the pipe has quadrupled. Next, the area of the pipe has increased by a factor of 4, so that means that the velocity has decreased. So area of 1 times the velocity of 1 is equal to the area of 2 times the velocity of 2. So since area 2 is much larger, it's 4 times larger, then that means velocity 2 must be 4 times smaller. Because the volume of flow must be the same, the large area means that the velocity must decrease. So we've been asked to find the change in pressure, but to find that we need the velocity of the water. To get the velocity, we first need to find the area of the pipes. So I guess to start, we use the formula. The area of a circle is pi r squared. So we multiply pi times the radius squared, which is 1 meter. So that gives us 3.14, or pi meters squared. To find the area of the second part of the pipe, we repeat this using pi r squared again. So this time we multiply pi times 2m squared, and that gives us 4 pi, or something like 12.57 meters squared. All right, so we have the areas, so now we want to find the velocity. So the mass balance tells us that the area of 1 times velocity of 1 is equal to the area of 2 times the velocity of 2. So velocity of 1 is 8 meters per second times the area of 1, which is pi, and divide that by the area of 2, which is 4 pi. And so that means the velocity of 2 is 2 meters per second. That should make sense, right? The area increased by a factor of 4, so the velocity should decrease by a factor of 4, because the water, because the pipe is larger, so it has a larger area for the water to flow through. Okay, so now we have the velocities, so now we want to think about the change in pressure. We know that the velocity is decreasing. If the velocity is decreasing, then the kinetic energy has decreased. If the kinetic energy has decreased, then the pressure must increase. So we start by writing down our conservation of energy for a fluid equation. So the pressure at 1 plus 1/2 rho v squared at 1 is equal to pressure of 2 plus 1/2 rho v squared 2. We rearrange this to find the change in pressure. So P2 minus P1 is equal to 1/2 rho V1 squared minus 1/2 rho V2 squared. We previously found the velocities, so the change in pressure is 1/2 times rho, which is 1,000 kilograms per meter cubed, to 8 meters per second squared, minus 1/2 rho times 2 meters per second squared. So doing the math on this gets us that the change in the pressure is 30,000 pascals, or 30 kilopascals. So, and notice that this is telling us that the pressure has increased by 30 kilopascals when the area of the pipe has increased from a radius of 1 meter to a radius of 2 meters. The pressure has increased because the velocity has decreased. Because of conservation of energy, when the velocity of the fluid increases, then the pressure decreases, because more of the energy is in the form of kinetic energy. When the fluid slows down, then there's less kinetic energy, so that means the pressure increases. Okay, so we can use the conservation of energy to solve a bunch of problems. For example, if we have a hole in a bucket, we can set the kinetic energy of water rushing out of the hole to be equal to the potential energy at that depth. The reason you can do this is because as you move down, the pressure increases, converting potential energy into pressure, but then when the hole in the bucket is reached, then the pressure can be converted into kinetic energy. Your potential energy is rho gh, and your kinetic energy is 1/2 rho v squared. So the rho's cancel out, and you can solve for velocity. If we put a spigot on the hole and turn it up so the flow is pointing up, then the height of the flow will equal the top of the water line in the bucket. So you can figure out this out based on conservation of energy without doing a calculation. The pressure change is rho gh at the spigot, and then the pressure is converted into kinetic energy, and then when it leaves, it's converted into gravitational potential energy as it rises up. Bernoulli's principle, that when the velocity of a fluid increases, the pressure decreases, is a surprising result, but it appears in a number of phenomena. We've already mentioned flight, but this slide shows how prairie dogs can air condition their burrows by making one high burrow that the wind rushes over. This lowers the pressure and pulls air out of the burrow, creating a flow circulating the air. Another darker example is an embolism. If an artery is blocked, the velocity of the flow decreases, which causes an increase in pressure. This increase in pressure can then lead to additional damage. Third example is the damage caused by a tornado is often caused by the roof of a home being ripped off because the high velocity of the wind results in a large reduction in pressure, so the roof is ripped off by the higher pressure inside of the building. Okay, so you have a FET to look at from O-Physics, so you should play around with it a bit. I think it might help you visualize Bernoulli's principle. I don't think this one's embeddable, so click on the link. Also, you have a problem very much like the one we just did, so go ahead and do that. All right, so I think that's it for our unit on fluids. So next we're going to take a look at rotation. All right, good luck and take care of yourselves.